Questions? Yeah, question. Equations you'll need to memorize. Let's see. What have we had so far? We've had the electric force, F is equal to Q times E. We've had the electric field due to a point charge, 1 over 4 pi epsilon 0, Q over R squared times R hat. And what's new that you will need to memorize is the magnetic field of a point charge, mu naught over 4 pi QV cross R hat over R squared. Okay, so that's the only new one for this test. So memorize. What I'm going to do today is I'm going to move pretty quickly and kind of do a little whirlwind tour of the most of Chapter 20, which is on basically relating everything we've talked about in circuits so far to macroscopic properties. Okay, so we have talked about capacitors, and we'll deal a little bit more with them today. But the other big theme of this chapter is that we've been dealing a lot with things like electron current, little I, drift speed in circuits, speed of mobile charges in metals. We've been looking at the electric field inside wires. These are all quantities that are important, but sort of relate to our microscopic picture of circuits where we have individual charges moving through a metal, surface charges which create electric fields inside the metal which drive currents. Okay, and of course when you're dealing in more practical applications, we tend to think about quantities like potential difference, which we've talked about, conventional current, which is something that we can easily measure with a meter. On this side we've had things like mobility, and so these are micro quantities. On the micro side we've had mobility and electron density. On the macro side, it's easier to deal with quantities we'll call resistance, which you probably have heard of, and something called conductivity, which we'll define in just a second. Okay, so we're relating the same quantities we've been dealing with. We're relating the same phenomena we've been dealing with, but sort of recasting it in terms of macroscopic quantities that are easier to measure and more often dealt with in practical situations. So we're just kind of go through this in a whirlwind today. Before we get to resistance and conductivity, I want to talk about something called capacitance. So we looked last time at charging and discharging a capacitor, and it turns out that the amount of charge that can be stored on a plate of a capacitor, so again we're talking about a parallel plate situation, and one side gets charged positive, the other side gets charged negative. The magnitude of the charge that can be stored on one of those plates, called Q, is proportional to the potential difference across the plates, delta V, and the constant of proportionality is called capital C, and capital C is the capacitance. So be careful, this doesn't mean coulombs now, this is some other quantity called capacitance, and so by definition it is the charge divided by the potential difference. Okay. What does it mean? Well, first of all, it's measured in units of coulombs per volt, and that's defined to be 1 farad, named after Michael Faraday, famous English physicist. What does it mean? It's essentially saying, again, how much charge can you store in a capacitor given a particular potential difference across it? And it is related to only geometric properties of the capacitor itself. Okay, and the way you can show that is that, let's say you have a parallel plate capacitor and you want to calculate the capacitance of it. So here's a capacitor. And it's got a separation between the plates, call it S, and it has an area of the plates, call it A. And there's an electric field in here. Let's say this is a positive and negative. The electric field is pointing that way. So that's the field inside the capacitor. I want to say that the capacitance then is equal to the charge on one of the plates divided by the potential difference. So that would be the charge on one of the plates divided by the magnitude of the potential difference. If the field inside is essentially uniform for a very large capacitor, it's just going to be the field times the distance, right? So it's going to be the field of the capacitor times S. We have a formula for the electric field inside a capacitor, right? The field inside a capacitor is Q over A over epsilon naught. So if I plug that in, I have the capacitance then is Q divided by Q over A over epsilon 0 times S. And so let's see if I rearrange this a little bit, bring the A downstairs, have something like that. And so this becomes epsilon 0 A Q over QS, and the Q's cancel out. And so I just have a fundamental constant, 8.85 times 10 to the minus 12, times the area divided by S. So it says that the capacitance only depends on the area for a parallel plate capacitor, only depends on the area and the separation. The bigger the plates, the more charge you're going to be able to store. So you have a bigger capacitance. The smaller the gap means a smaller potential difference for the same amount of charge. So if you make the gap smaller, you'll have a larger capacitance. And let's actually reference back to something we were talking about last time. We were talking about the fringe field of a capacitor. And so let's just make a connection here. Think back to what we talked about when we were charging up the capacitor with a battery. We had said that the final or the point where you reach static equilibrium again is governed by the point where the fringe field of the capacitor, so if this is negative and this is positive, the fringe field, this is going to charge up negative. The fringe field of the capacitor will be pointing that way, and the field due to the battery and the surface charges will be pointing the other way. When those two equal each other, we reach a point of static equilibrium again. Okay, so let's think about you have two capacitors initially uncharged. The only difference between the two is that one has larger plates than the other. Okay, so capacitor, I don't know if you can read the numbers here, but capacitor number 2 has a big, large plate. Capacitor number 1 has a small plate. They both have the same distance between the plates. After 0.01 seconds of charging, what can you say about the fringe field? And here's the formula for the fringe field. The fringe field is Q over A over epsilon naught times S over 2R. Worked that out a while back. Okay, so the bigger capacitor is going to have the smaller capacitor has a larger fringe field, and therefore the bigger capacitor has a smaller fringe field. So what does that mean? Which one is going to be able to store more charge? The bigger one, right? We said that the fringe field determines when the charging stops, because once the fringe field gets large enough to cancel out the field due to the battery and the other surface charges, you're back to E net equal to 0, and no charge is going to flow. So if you can keep that fringe field smaller for a larger amount of time, you're going to have more current flow onto the battery, and therefore you're going to have more charge or excuse me, more current flow onto the capacitor, and therefore you're going to have more charge stored on the capacitor. Okay, so arguing it from the fringe field is kind of verified with the arguing it using the capacitance, because it says that the bigger the area, reducing the gap size would also reduce the fringe field, so that would also increase the capacitance, leads you to store more charge on the capacitor given the same potential difference. Okay, so in one case we're arguing in terms of field and fringe field. The other terms we're arguing in terms of capacitance and change of potential. We get the same result. Okay, let's just try a quick calculation, real simple. You have a 0.5 farad capacitor connected to a 1.5 volt battery and a light bulb, and then the current runs until the bulb goes out. What's the absolute value of the charge on one plate of the capacitor once we've finished charging it up? Okay, it's got to be 0.75 coulombs, right? Just plugging this in. The point is that, I mean, this is simple, right? Just plug and chug. But the idea is that if you have a capacitor that's charged up, the current's no longer flowing, the loop rule still applies, right? We can still go round trip, potential difference has got to be equal to 0. So if I have if I'm going in from negative to positive, I have a 1.5 volt increase in potential as I go across the terminals of the battery. There's now 0 electric field in the wires, 0 electric field in the light bulb, okay, because we're at static equilibrium again. But there is now an electric field across the gap of the capacitor pointing in that direction. Okay, so if I go in that direction, there's a potential drop, so that's going to be positive 1.5 volts across the battery minus Q divided by C. The potential difference across the capacitor equals 0. Q over C is 1.5 volts, so Q is going to be C times 1.5 volts, or 0.5 times 1.5 volts, which gives you 0.75 coulombs, okay? 3/4 of a coulomb. Is that a lot or a little bit of charge? That's a lot. That's a huge amount of charge. How much charge was stored on one of your charge tapes from way back at the beginning of the semester when you're doing the tape experiment? About how much? 1 times 10 to the, what was the exponent? Anybody remember? -9, -8, something around there. Yeah, it was like a nanocoulomb or a few nanocoulombs. Okay, so that's a billion times more. Okay, we're talking about a lot of charge. So a farad capacitor, a 1 farad capacitor, is actually pretty extraordinary. It can hold a lot of charge. Well, on one of the plates, right? The net charge is what? The net charge of the capacitor is what? 0, right? We're just talking about a charge separation between one side and the other. But still, there's a lot of charge on one plate. This little black capacitor that was in this kit that we were using last time and which you'll use in lab, this is a 1 farad capacitor. So it can hold a lot of charge. The drawback is that it's only rated at 2.5 volts. If you have too large of a voltage across it, you increase the electric field so much that the capacitor is no longer a capacitor. The material in between, the dielectric, is no longer an insulator. It becomes a conductor, and then you get current to start to flow, and then you have a pretty awful capacitor, and smoke starts to come out, and that's when you know things are going bad, right? So you're not going to do that in lab. No, you're not going to burn up the capacitor. So, but that's the drawback, okay? All right, so that's capacitance, and that's basically all I'm going to say about that.